Section 5.2, the characteristic equation. In the last section, we found out what eigenvalues and eigenvectors were. In this section, we're going to look at a method for finding eigenvalues using what we call the characteristic equation. Let's recall what the definition for an eigenvalue is. If we have an n by n matrix, so a square matrix, we say this lambda is an eigenvalue of A if there exists a non-zero vector x such that A times the vector x is equal to this lambda times the vector x. We say that x is the eigenvector of A. So if this equation here is true, we can subtract the lambda x from both sides, and we notice we'll get the zero vector. And then, of course, we saw that, if we take out this x that's in common, we must, so that we can actually subtract these matrices, multiply I, the identity matrix, by our scalar x so that we'll have a matrix minus another matrix in the same form. But what can we say about this here? We know that we must have non-trivial solutions, otherwise this x would have to equal to the zero vector. But we've stated that we must have a non-zero vector x, so therefore we must have non-trivial solutions to this equation. So, if A minus I lambda times the vector x is equal to the zero vector has non-trivial solutions, what does this mean about the determinant of this A minus I lambda? If we are saying that the determinant is equal to 0, then what does that tell us about A minus I lambda? It should not be invertible. If it were invertible, then we know that the determinant cannot be equal to 0. So therefore, A minus I lambda should not be invertible. Now, let's find the eigenvalues of this matrix A. And we're going to do this by using the determinant. So given this matrix A, the first step we want to do in finding the eigenvalues is to find A minus I lambda. We saw from the last section, this can easily be done by just subtracting lambda from the diagonal of the matrix A. Our next step is to find the determinant of this matrix A minus I lambda and set it equal to 0. So, of course, this would be the determinant. How do we find the determinant of a 2 by 2? We take these entries, multiply them by each other, minus these entries multiplied by each other. And now we expand. Doing some algebra, multiplying through, we get this here. Negative 6 minus 3 lambda plus 2 lambda plus lambda squared minus 6. Okay. Combining like terms, we get this here. Then we can factor our equation, and we notice that we have lambda is equal to 4 and negative 3. So these are our eigenvalues for this matrix A. If you recall, this is the same matrix that we saw in the last video where lambda is equal to 4 was given to us, and we found the eigenspace. Okay? So now we have a method of actually finding how can we find out what all the eigenvalues are. So that brings me to a definition. If a scalar lambda is an eigenvalue of an n by n matrix A, it is a eigenvalue if and only if it satisfies what we call the characteristic equation. And so the characteristic equation is the determinant equal to 0. So if we look back here, we notice that this here represents my characteristic equation. So let's consider this matrix A here, a 3 by 3 matrix. And what we want to do is to find the eigenvalues using the characteristic equation. So to do this, again, we want to find A minus lambda I, and we do this, of course, by subtracting lambda from our main diagonal. And now we want to define the determinant of this matrix, this new matrix A minus lambda I, and set it equal to 0. And of course, when we have a 3 by 3 matrix, we need to expand about a row or a column. So since I have all mostly zeros here, we'll expand about the first column. Doing this expansion, I have 1 minus lambda times the determinant of the resulting 2 by 2. And of course, to find the determinant of this matrix, we'll multiply this time minus the product of this. We notice we'll have this resulting matrix here, which is our characteristic equation. And simplifying, we notice that we will have lambda equal to 1, 3, and negative 1. And I don't know what that last line is here. 1, 3, and negative 1. And notice if we think back to our previous section, we say that we have a rule that says if I have a triangular matrix, then the eigenvalues will be the entries along the diagonal, 1, 3, and negative 1. And when we actually use the characteristic equation, this validates that indeed we do get the same values. For this example, we want to find the eigenvalues and eigenvectors using the characteristic equation. So of course, first we want to find the determinant of the matrix A minus lambda I. Notice our matrix A looks very similar to the one we just did, but this time we have a 5 in this entry. So when we expand about the first column of this matrix here, when I do the determinant of this here, it'll be 5 times 1 instead of 0, and so we have an extra entry of 5 here. Now we want to do the algebra for this. So here we will expand what is in our brackets. Adding our like terms together, we get this here. And then simplifying, we get this expression here, which is a simplified form of our characteristic equation. And we notice that lambda will be equal to 1, 4, and negative 2. So these here are our eigenvalues for this matrix. Now again, given this matrix A, we found that the eigenvalues were these here, 1, 4, and negative 2. Now we want to find the vectors for each of these, the eigenvectors for each of these lambda. So let's look at when lambda is equal to 1. When we do A minus I lambda, of course, since lambda is 1, that's just A minus I, which means that we subtract 1, which is our lambda, from each value in our diagonal. So we get this new diagonal here, which is our original diagonal minus 1. Our next step is to row reduce. And so we want to actually put this in RREF. In doing so, we have this equivalent matrix here, with a pivot being here and a pivot being here, which tells us that x1 will be a free variable, x2 we see is equal to 0, and x3 is equal to 0. So if we were to write our eigenspace, we would get x1 times the vector 1, 0, 0. This is our eigenspace. But we're looking for the actual eigenvector, and so the eigenvector would be the space that spans this matrix 1, 0, 0, 1, and so therefore our eigenvector is 1, 0, 0. For your reading assignment, I would like for you to find the eigenvectors for the two remaining eigenvalues for this particular example.